Let me start recording. All right. So I saw that only few people have attempted the last session's problem. This one. Okay. So do you have any questions for this before we start the discussion of the last problem? Okay, so regarding this problem number 2, basically we are given a huge text, very huge text, and we have to formulate the next word's recommendation. All right. So we have to prepare this kind of recommendation. And so is there a doubt in the question or is the question clear? All right. So I'm assuming the question is clear. So, all right. So the first approach, a simpler approach would be that out of each sentence, we pick all two consecutive words and make the first word as the key. All right. So in case of, as you can see that how and R and U, and then Ram and happy and birthday and to you. All right. So what will it do is that in case there is another word following how, that will also come here. Okay. So in case you have happy new here, okay, so that will also come. So here will be you and happy. So I'm just sticking to what I'm proposing, and all right. So this is my solution, the solution I'm proposing. Okay. Now after this, basically happy, birthday and happy new has got the same key as happy. So birthday and new will come together, which means after happy it can be birthday or new that can follow, right? So do you think this is a good approach? So, right, so basically what I'm trying to do is I'm trying to form the pair of words, and then first word is the key and second word is the value. And all those values, all those second words whose first word is same, they will come together because that's what MapReduce does, right? And then once we have that, then we can do the frequency analysis of the words, as in count, do the word count on the values for each key and then form it. All right. Now, do you see any problem with this approach? Yes. Is this approach clear to you? Am I audible to you? Ajit, Abhishek, Ankush, Apurv, Harish, Casey Reddy, Rumen, Valentin, P. Malik, Manish, Vinay, Vishnu. Alright, so am I audible to all of you? So my question to you is this approach clear? All I'm trying to do is create the pair of words, since our overall objective is to guess the next word that could come. So first, for each word we do the calculation that what are the next word which can follow it, and then out of all those next words that can follow a word, we'll do a word count, and the top five most frequent words, we'll list them down. Okay. Yes. Yes. So Apurv, you are right. P. Malik, you're right. That is one problem. Right. Casey Reddy, that's a good point. Any other problem do you see? So shouldn't we forming a pair called birthday Ram? Sorry, birthday 2. So shouldn't we there a pair in which we have birthday and 2, where birthday is the key and 2 is the value? Any other? I'm actually looking. I can at least see 3 to 4 problems in this approach. So mapper will form the key values out of pair of words, two consecutive pair of words, and reducer will do the frequency analysis. All right. If the word reoccurs, which word, Papi Malik? Right. So if the word reoccurs, like the way in the key the word happy has reoccurred twice. So new and birthday are the two suggestions when user types happy. For happy key, we have got two values, birthday and new. Had birthday been 100 times and new been one time, and there are other more words. So we just pick five most frequent word that follow happy. Okay? We just pick five most frequent word that follow happy. Instead of all the words, we just do a word count in that, in the values that follow happy. Right? Now, any other problems? I agree that Ram and Happy shouldn't be the pair, but okay, so that is one mistake in this approach. Second mistake, I think, from this discussion is birthday and two should form a pair because two is following birthday, right? So new line shouldn't be the criteria. That is second problem. Any other problem? I see one more problem in this approach. Birthday and two should form a pair. Ram dot happy shouldn't form a pair. There is one more problem. Anybody? Anybody? All right. So let me kill the suspense. So here the other problem is that frequency analysis computation should not be done by the reducer. Instead, you should be forming tuples, and and think about it. If you try to basically the frequency computation, because there could be millions of words following a particular word, say the, to, or any such, right? All right. So yeah, Valentine is right. URAM should also be there. So the computation of frequency which is happening in the reducer, we have to further make the map reduce out of it the way we have done a word count problem earlier. All right. So that's another topic altogether, but we will stick to these two problems right away. First, basically, the last word of the line should pair with the first of next line if the sentence has not ended. Okay. So that is the point of discussion today, that how do we make that happen? Okay. Now, all right. So we'll go into the details of, so which means that we'll have to do sentence by sentence processing instead of line by line processing. So MapReduce, each mapper get one line at a time by default. How can we make it happen such that we can choose that we can customize that behavior of Hadoop to give us to give us say 3 line at a time, one paragraph at a time, or one sentence at a time. So that is what we are going to discuss today. All right. So you understand the problem here. Since our mapper at a time will get a single line, say how are you, here in this sentence you can see how are you, this is what we are going to get. Now, but what we want is we want the whole sentence up to how are you, Ram. Okay, that's not the default behavior of MapReduce. By default, MapReduce will only give us how are you at a one time. Then in the second mapper, when we are applying a mapper, we'll get a input line, right? So we'll right now by default we'll only get one line at a time. Okay. Now then, okay, so that's what we are going to discuss. Before that, let me just quiz you a bit. Okay, so the data generated by mapper is given to reducer and then it is sorted and shuffled. Is it yes or no? Okay, Rumen and Vishnu is right. Good. So the data generated by mapper is first sorted and shuffled and then given to reducer. Okay. All right. The next one, the mapper can only generate a single key value pair for an input value. Yes or no? Good, good. Rumen is right. And good. P. Malik is also right. So the mapper can generate many number of keys and values out of a single input. Okay. So if you remember our word count example, where we were given a single value called whole line and we broke it into multiple key values, right? Make sense to you? All right. All right. So let me put a question mark before I ask a question. All right. By default, there is only one reducer in case of a streaming job. Yes and no. The answer is yes. By default, the whole reducer, sorry, in case of a streaming job, there is only one reducer, but you can configure it. All right. So you remember streaming job where we passed our script name as well as we passed our command name and then we processed the data. We used our existing commands to do the map reduce. So in that you can customize number of map reduces by typing this on command line by saying -d mapred dot reduce task dot reduce dot task equal to 10. So that will create 10 reducers. Okay. Again, I'm putting a question mark so that I can differentiate your answers. All right. So what is the role of job tracker? Executing MapReduce logic or delegating the MapReduce logic to task tracker? Okay. Good. Good going. Okay. Harish. So there was something called task tracker and there is something called job tracker. So what is the role of job tracker? Good, good. So probably only Harish got it wrong. Okay, all right. Can't blame Harish because the names are little confusing. All right, good, good. So everybody is with me. Now let me put another question mark. All right, all right. So map map logic is executed preferably on the nodes that have the required data. Yes, yes. Great. All right. So everybody is with me on this. Great. Great. Next question to all of you is the whole of the chunk available on a node is fed to the mapper. Okay? Okay. So could you support your answer? Then what is it that is fed to the mapper? Okay. All right. Yes. Yes. So interestingly, all of us have answered it correctly. No, but the reason is a little bit different. Okay, so as Vishnu says that because if you think about it, I'll we'll go back into go back into the details into this question. Okay, so this is going to be our agenda to explain why is it. So the whole of the chunk, okay, generally whole of the chunk approximately is fed to the mapper. Okay, and but how, that is what we are going to discuss. Okay, so input in very very here I'm going to say the sentence, even if it doesn't make sense to you, don't bother. So input is split using input splits, and part of which is transferred to other mappers. We'll talk about this today. Okay, whole chunk as in Manish, the whole chunk means 128 MB of the data. Okay, so when we split the file, we are talking about that whole block or whole of the block. We can say HDFS block. Okay. All right. So now we'll talk about this particular question in a minute. In a minute. Now, question to you is, where does Hadoop store the result of reducer? In HDFS or local file system? Good. Good. All right. Excellent. Now, let me just put a quick question mark. Where does Hadoop stored the intermediate data such as output of tasks. Okay. Okay. So this is the question where the answers are probably equal to all 3 points. Okay. So Rumen says that memory are local. Okay. Okay. All right. So the answer is file system. Although file system is not a straightforward answer because the data, intermediate data of map tasks is pushed to the memory, which is being spilled over continuously onto the file system. Okay, we call them memory supported. Sorry, file supported memory. File supported memory. Yeah, there is this. Just like paging, there is a very good term for this. I'm just forgetting that term. Okay. So the answer is not very straightforward, but we can safely say that it is stored in the file because the whole output cannot be stored in the memory. Okay, because map have to handle hundreds of gigabytes of data sometimes, and that whole thing cannot be stored in the memory. Only part of it is stored in the memory, which is pushed to the disk immediately. Okay, so we can't say really that it stores in the memory. It doesn't persist in the memory. Okay. Yes, local file system, you're right. We are referring to local file system. I can write it specifically here. Okay. All right, so okay. Okay, so generally it is done first. And why is it so? First, let me discuss why it is not in HDFS, because this is a intermediate data, and this data is of no use after this job is over. First, because we want the output after our reduce has run on it. Second, this data is only partial. Okay. So therefore, there is no point in retaining the output of maps after the work is over. Therefore, therefore, there is no need to keep it in HDFS, because if we try to keep it in HDFS, it is going to be backed up and there are versions maintained and there are whatnot. So there is no point in worrying about this data. Okay. And in case the local file system fails, the task tracker will fail and the work will be delegated to other nodes. So nothing to worry on that front. Now, why not in the memory? Had it been only in the memory, in case that in case the data is huge, where are we going to keep it? So the whole data cannot be put into the memory. It is always put in the memory for few seconds and then pushed out to the file system. All right, great. So we are all almost on the same page. So if anybody has doubts, then just ping me and we can discuss. All right, good, good. So recording is being done. Yes. Any questions on this, Shilpa, Manish, Ruman? And Abhishek? So Abhishek, you got the answer. Why should it be the on the all right. So okay, okay. Good, good, good. Moving on. All right. So before we go on to the input split, this particular portion, we'll just go over the MapReduce in Java. So last time we had gone through a quick example of MapReduce in Java. So the flow was, let me just open my Eclipse. So when you are writing MapReduce in Java, why should you be doing it? First, Java is the language in which Hadoop has been written, but also Java is very popular language. So Hadoop guys thought of supporting Java primarily. Okay. Second, and therefore the APIs provided by Hadoop guys were mostly and most extensive and highly covered in Java only. So you could modify Hadoop's behavior to a very large extent using Java. Okay, to a very large level, you can use and yes. So probably Python would be the second most popular language to write MapReduce in. Okay, so this is what my understanding is also, but I cannot support it with numbers. All right, and yeah. So if you have to write MapReduce in Java, these are the few steps. First, install any Eclipse and any Eclipse that has Java in it. Okay. So whether Eclipse for J2EE or Eclipse for Java programmers or any kind of that Eclipse will do for you. Second, create a fresh Java project. All right. Those who do not have. So go to File, New, and say Java project. Once you have done that, there are sorry there are once you are done that, there are various libraries which are I have attached, and also those libraries are available when you download hadoop.zip. Okay, hadoop.tar.gz. In that is it's available, and also in case of our project I have made that available to you. Okay, so I'll make one Java project available to you. You can download the libraries and add it to your project. Okay. So how do you add libraries to the project? You go here. I'm sorry, let me just close this. Yeah. All right. So we have got this. So if you go into right click and say properties, there you have something called Java build path, and there you can add external jars. Okay, right now I have added this. So this whole project is what I have already. I'll be sharing it if it's not already done. Okay, and then change your JDK from 7 to 6. Why? Why do we need to change your JDK to 7 to 6? Mainly because when you are coding, you should be compatible to the lowest version of Java you want to support. Okay. So generally, as of today, also there are lot of Java 6 installations are there. And in case your code is written in Java 7, then when it compiles, it wouldn't run on Java 6. Okay. Same is case with in case you are running creating your compiling your code which is compatible to Java 6, it won't run on Java 5, but it will run on Java 7. Okay. All right. So every class file, in case it is compiled for X version, it can be run in any Java version which is uh, newer than X. Okay, which is like saying somebody has coded given you an old program and the Java has been upgraded, so it still runs. Okay, so therefore you generally tend to be little supportive of the older versions also, because there are many think from the people who have installed Hadoop in your organization. They may not have upgraded their Java to 7. Okay, the Java might still be running on 6. In case you are fairly confident, then you should be basically supporting. Say you are fairly confident that hey, your organization has Java 7, then you should put it in Java 7. No, Java 6 does not have any problem with the Hadoop 2. Yeah, it perfectly runs. And even if you make your code compatible with Java 5, that will be also running with Hadoop 2. Okay, that is the good part about backward compatibility in JVM. And okay, so more important than that is basically you go to right click properties and then say Java compiler, and here you change it to 1.6. That's all. Okay, you change it to 1.6. That's what I'm talking about, making it compatible with the previous version. Okay, although I prefer JRE6, but you can have uh, you know so you can, this was default, this is also all right. So any version of Eclipse will do, any latest version or even couple of years older version of Eclipse will do for you. Nothing to worry on that front. So almost all Eclipse will do. If you have existing installation, that's also fine. So any Eclipse which has Java with it, so that will do. Now, what are the things you need to do after you start your Eclipse? So you created a fresh project. Now you create maybe a package like I have created. Have created a src folder. You can say new folder. And for this example, you can simply import the project which I have given. And how do you can import file and then you can say import. And the folder I'll be giving, you extract that folder, keep it somewhere, and then import that into that. They'll create the whole project as is. If that's not the case, you can create a new folder, src, and then you create a new package. You'll get sg. Inside that, you say new class. Okay. So first we are going to create a mapper. All right. So basically, this is a class. Okay. This is a class, and what does it have? And these are the imports, as you can see. Okay. So while creating your class, you have to extend a class called mapper with these template values. Okay, what are these template values? It says that this mapper is expecting this as input, as in object is the key and the value is text. Okay, because the mapper in Java gets, if you are giving the file as input, the the key is byte count, the object is the byte count, and the text is the each line. That's what the mapper gets. Okay, and we are saying that our mapper will be giving out key values as key will be text and value will be long writable. Okay, this one. All right. Once you do that, it will generally ask you to implement a map function. Okay, or you can basically create your map function like this. Okay, this is the definition, you put override on it, and whatever type of the value you have defined here, that you are expecting object and text as key value, that you will be writing here, and based on what you have defined as output here, that is what will go into context write. So output is text, okay, and value is long writable. All right. Now, so first thing you do is you define a step mapper. All right. So most likely your output is going to be common. This is like general skeleton. This is a general skeleton of your program, and this is your code. This is your code. Okay. So, and remember here again, we are doing the same example of word count, just that a little bit cleaner version. So, the line, the input text is given to us as the second argument of the mapper. First argument which is given to us by Hadoop is the byte count. Okay, byte count of this particular line, right? And so the first thing which we do in this program is this line. It says, take this value, convert it into text string. To string basically gives you the actual content of the value, and then you split that value. You split that value based on space or tab. Okay, this is a regular expression. Those who have not attended my regular expression session, I'll send it to you so that you can attend that. Okay, or maybe I'll mention, put it in the session 3 itself. All right. Now, so value, the line is split by space and tab. This regular expression says that a, a tab or a space and any number of times. Okay, that's what this regular expression says. So we split our input line based on spaces. Spaces can be tab or space, a combination of tabs and spaces, and all that, right? And that will give us word. And for each word, this basically we say that for each word out of words, what we do is we replace any non-alphabetic character with nothing. Basically, we are removing non-alphanumeric character from our word, comma, dot, dash, double quote, single quote, and all that we are removing over here. And afterwards, we are converting into lowercase, and that becomes our clean word. And after we get the word, we put it in the output. So we tell our context that this is our key, the word which we have prepared, and one as in number one as the value. Right? Okay. Okay. So Vishnu, yeah, that I am actually working on so that I can prepare a very small crash course on Java basics. Okay. So I'm actually working on that. All right. Let me just make a note of it. All right. Now, So this was our stub mapper. In this, all we did was we were given key values, and we have formed new set of key values. Basically, it sounds awkward that in mapper itself we getting the key value. Here, key is just the byte count. Byte count is nth byte. Our value is starting at nth byte. So this line is starting at this particular byte. That is what it is. Okay, so we are given one line at a time. We formed our key values and put them into the context. Okay, instead of printing onto the screen, we have put it in the context. All right, so this is clear to all of us. Now the next step is, yes, so these data types are basically created. The object is the general one, which is there in Java by default, but long writable, text, long writable, these are created by for Hadoop specifically. Okay, these data types are created for Hadoop. Okay, these are basically classes which the standard philosophy of Java that you can create your own data type by defining classes. Okay. Next step is that you create a reducer. Okay. You create a reducer where if you see this key value will be what, here the output key value of mapper is text and long writable. So basically when we are defining a classes, we are saying we are defining here we are saying we are defining a mapper which will have key and value of this type, input key value and output key value of this type. Similarly, when we are defining a reducer, we are saying that our input key value is a text and long writable, which of course will be exactly same as what is the output key and values of our mapper. Okay, and then we define that what is our output key value of reducer, and this is what it is. Okay. All right. So we have got reduce like this, and that, and in this reduce we got values and array as an array. This is an array, and key as as the word. Now we iterate over all the values, we just sum them up. So here what we are doing is we are iterating over values, and we are summing up all the values and then printing it into the context. So the way our mapper or reducer talks to the system is by the way of context. This context class is where it puts the output. Okay. Now that is our reducer. Now we create something called a driver. Now we create something called a driver, which basically ties all of these things together. Driver is like our main entry point, which has a main function, and it says that start our jar. These are our input files, and this is our mapper class. This is our reducer class, and please do the job. Okay. So the driver, the actual here I have trimmed down the code. The actual code looks like this one. Here you have got, first we define something called a job on top of the config, and for job we say that this is my, okay, this is my mapper, this is my mapper, this is my reducer, my output is these are the output data types I'm expecting, and here there is something called partitioner. We'll talk about the partitioner also at later point of time today. Okay. So, and here number of reduced tasks. How many reduced tasks are going to be there? Let's say two for time being. Okay. And once you are done with this, the next step is that you export the jar. Okay. You select the project and then say export, and then you say jar file. All right. And put a name for this, and there we go. All right. So it has exported the jar file. Next step will be, okay, once you have exported the jar file, you will have to copy it to the Hadoop server. So anybody quickly who can tell me that how do you copy the file to Hadoop 1.no big data? Has anybody tried to copy the file to Hadoop 1.no big data? Yep. So WinSCP is the one which you can use. Okay, on Windows. Thank you, Vishnu. So has anybody used WinSCP so far? Vishnu, have you used it yet? Okay, okay. So here I am going to copy my jar to Hadoop 1. So I say scp, and then there is word count dot jar. I say student at Hadoop 1 dot no big data dot com, and then I say colon. After colon, you can put a directory in which you want to put it. Okay. So for you, okay, S- is it done? I think it is done. Yeah. So this is my, so SSH. So in case you're on Windows, you might do putty. So I'm logging on to my server. And this is not something specific to our no big data. These are the standard ways of connecting SSH and SCP. And in case you have a lot of data, you should prefer rsync in case you are synchronizing data, that remotely synchronizes the data. Now let me go to my own folder. So here we go. Here you can see our word count has come here. Okay. Now java dot jar, I say word count dot jar, and I say sg dot stub driver. So when this is the standard syntax, Java, so not Java, we have to say Hadoop. Okay, so Hadoop jar word count dot jar, and your the name of your driver. Okay, and let's have a look at. So once you have copied it using this, and in case you have more libraries to copy, say you want, and also note that every program, every Hadoop program is a standard Java program. Okay, which means it can send emails, it can itself write to the databases, okay, if it wishes so. It can also write to any file system, and it can do anything a Java program can do. Okay, so you remember that part, because I recently got a query from one of my brilliant students that can I write the data to MySQL from MapReduce? I said yes, of course, because that's a standard Java program. But you should avoid it because it is going to hit your database really badly. If that is okay for you, then you should go ahead. Okay. And all them and because these mappers are going to be run at multiple machines parallelly, so you will have to take care of the scenarios where two mappers are trying to write or read the same data to avoid the deadlocks. All right. So you can use minus use lib to basically supply all the jars you want to include. Okay. Or you can do a basically like this lib jars. Earlier using lib you could only give a single jar file, but thanks to the recent changes now you can specify the whole list of jars like this. You can say minus lib jars and then all right. Now okay, now you can run this way. Is there context outside mapper class that is available to map? No. Yeah. So Ajit's question is that is there something, some variable which is available outside of the mapper class, the outside of the context, the way basically he is seeking for some way to communicate with other mappers. Right. Right. So the answer is no. Okay. But you can use a central mem cache or you can use a central service and use their service API and talk to that one. Okay. All right. But you shouldn't be relying on basically first whenever you're building MapReduce, the first tendency is to have a central state with which they can come all the mappers can communicate. Okay. But first try to avoid the situation where mappers need to communicate with each other as much as possible. Okay. Although it is possible, but try to avoid mappers communicating to each other. Try to model it using MapReduce itself. In case you cannot figure out a way of one mapper communicating to another, try to make multiple passes. Okay. If that is also not possible, then think of something by which they can communicate. All right. So let me just try to run it. And as we saw in our code here, where is our this one? We are expecting the zeroth argument as the input path and first argument as the output path. So we will provide our input path. Input path is of HDFS. So let's have a look at our HDFS. All right. So in skiri, this is my HDFS folder. Skiri, there is a word count example and there is an input folder. So this is the file which we want to use. This big text is the one which we want to use. And where did it go? I say word count slash input. Okay. And where do I want to keep the output? As Giri slash word count, and I say output November 30. All right. So let's see what does it say. Oh, it is stub driver, not stud driver. This is the class name of what we gave. Okay. SG is my namespace or and or package name, and then stub driver is. So it has started the work, and when it starts the work, it gives you a URL to track. URL to track. You can see that URL here, and you can also see clearly that it tells you how many MapReduces are there, what is going on with the MapReduce job. And remember this, we have a total number of reduce. We have defined how many? 2. Okay. By if you don't define it, by default it will be 1, and it will do some sort of intelligent figuring out based on the size of the input. So if you so it is done. So it tells you exactly this is the debugging information which you will find quite useful while optimizing the performance. Specifically time taken here, there is a total time taken. Okay. So specifically you should take note when you're trying to optimize your process, then you should make a note of all these numbers. Okay. So it is done. And where did we keep the data? We said we wanted to keep in the word count and under this folder. So there are two parts. Why? Why there are two parts? Anybody? Part 0, part 1. Yes. So this is something important because the output of each reducer is happening parallelly, and that happens via in two different files. Okay. All right. So this is what we get. Okay. So this is the word count of each of the word. Let me just go to the last block. As you can see, our first block, and then we go to the next, next, next. All right. Okay. So this it has done the word count of all the words, but the important thing is it is not sorted by this value. It is not sorted by this value. Okay. It is sorted by the key. Okay. And also as part of your stub reducer, right? You could write the key first, long writable first, and sorry, the value first, the total and the word count. Okay? It is up to you. So let's say Hadoop cat, Hadoop fs, and cat is something which prints the file instead of using our hue, the web interface. We are using the command line to print what is there in our word count slash this is our folder, and okay, if we do So all I'm trying to do is I'm trying to find the find most popular word. Okay. So as you can see that in this, the is most popular word. It has come 80,000 times. Okay. Then off has come 40,000 times. And still there is space or tab left somewhere. I think it's some, yeah. And, and if you skip all of this, all of these standard words, okay, if you skip all of these standard words, then you will notice, you will notice these characters, okay. And in case you have just made a list of all the popular words generally and remove those, you can quickly figure out what is this story about. So Prince, Pierre, and then okay, Natasha, for example. So and Andrew. So it shows you quickly that this story is about Natasha, Andrew, and Pierre, and so on. Okay. All right, so we have got that. Good. All right. Now, the other important part which you should know is that whenever you are coding in any language or whenever you are programming the or even I mean whatever you build, you should build against test cases. Build it against test cases. Okay. So we call it test-driven development. So in Java, because if you saw the process, we wrote some code, then we exported it, then we copied it to the server, and then we ran it, we saw the output. It's a little longer process. And it might, I mean, you might feel it too big a task, and therefore you may not like to test things very quickly. Okay. Therefore, Java has provided you really nice way to test. So you write your tester. This is the standard code for writing test. Okay. So you create your class. You create your class like this, and then do a setup defining this is your mapper, this is your reducer class, and after that you start writing test cases. And once you are right, I mean here what I've written is I've just written failed fill everywhere except for this last one where all I have done is I've given my input and these are the input lines which I'm giving to the mapper and reducer for testing, and then I'm running it. Okay, so you can as run as JUnit test. Okay, so you can see that this reducer has failed because I have written that fail, and this mapper has failed while our test map reduce is worked. It has given the output where you can see the word count by using our logic. Okay, sounds good to you? We did not have to upload this and that just for the heck of it. Okay. So for example, here there are some special words. Just we wanted to test that whether our code is covering special words or not. So we can actually run it again like this. So it is covering that. So it has removed all of that from here. Okay. So it's running locally our code, and say we, for time being, we just removed this line. Okay. Where we are not removing, where we were replacing non-alphanumeric characters and lowercase, that line we have removed. Okay. So you will see these words also. You see that these special character and these special characters and also the capitals. Okay. So that the kind of, you know, basically it provides you the whole unit test case is providing you the quick way to test. Okay. Here, instead of just printing, you could have just uh, compared it with the pre-computed values. Okay. We call them assert. Okay. Assert true, assert false, so you could do that. Okay. So this is how you generally test your Java code. Is it clear with everybody? Okay. So we wrote a class called stub test. We defined our driver, map driver, reduce driver, and a combination of both. And then we set it up. And after we set up, then we start writing our test cases. For each cases, you define that this is your input. And note that we are not providing input file name. Here we are providing the input content. And once we have provided the input content, the next step is that we go. Next step is we run the MapReduce driver, and whatever output we get, we can do the asset. We can compare that is this word come this many times. Okay, so all of that we can do here. So the general strategy is you write your test cases first. Okay, although that's not how I demonstrated to you. Yeah, yeah, we do this way in the real time also. So we don't test on HDFS directly. You're right, because that's not something which is going to fail. What is going to fail is your logic mostly. Yes. So basically we call it these drivers, right? Map driver, reduce driver, map reduce driver. These are part of MR unit. Okay. These are part of MR unit. All right. MR unit is just a library for JUnit. Okay. Specifically for Hadoop. Good. Good. Are we good? Should we go ahead? So this is how you could create a quick test and run it. And this will give you the output quickly. And also, generally what you do is you define your input, you do the word count manually, and then whatever you're expecting as the word count, you will do that. Similarly, for every other problem, you will say specifically, I'm expecting this word these many times. I'm expecting this word in this many times, and so on. Here we have just printed it. Okay. All right. So that's what it is. Now, let's take a break a little early today, if that is okay with you. Okay, let's take a break for 10 minutes. Okay, back by Okay. Hi guys, I'm back. All right, so is everybody back? Should we start? All right, all right. Abhishek is there, Vishnu is there. I'm hoping that everybody is back. All right, all right. So good, good. Now, as we discussed earlier, that by default, our mapper is going to get line by line input. Okay, so at a time, our mapper will be presented with a single line, right? What if we want more than a line or less than a line? Okay, the way we had described earlier that we want sentence by sentence processing for our the suggestion for the word, the exercise in the last one. So what if we want what if we want sentence by sentence processing, or we want two sentences at a time, two words, two lines at a time? Okay, so to handle those kind of scenario, Hadoop comes up with an idea called input splits. Okay, Hadoop divides input into pieces called splits, right? While the way HDFS divides the input into blocks, Hadoop divides the input provided by HDFS into something called splits, input splits. Okay. For each split, there is one mapper. So one mapper instance for each split. Okay. And you can think of each splits. I I- I mean, and then each split contains many records. Okay. Each split contains many records, and mapper runs on each record of split. Okay. So split consists of many records. All right. And so you can think of it this way. So there is a mapper class which we created. It will be instantiated for one input split, and out of input split, each record will be run against each one mapper. Okay. So you can think of input split as number of lines, say 100 lines or 200 lines or 10,000 lines, and uh, out of these 10,000 lines, each line is being presented to the mapper at a time. Okay, so each line represents a record, while these bunch of rows, bunch of lines represent a input split. Okay, so how big a input split is, if you basically, that is up to you, how do you customize it? Okay, if you create too many small input splits, there is going to be heavy overhead. So each input split is prepared out of an HDFS block, and out of each input split, a records are prepared. Okay, so you can guess that in case you do a very small input split, there is going to be basically there is going to be too many input splits on each SDFS block. Then it'll be high overhead. Similarly, in case your input split is far bigger than the HDFS block, So for each mapper to run, all of this data will need to be copied to a single node. Okay, because then the mapper will be instantiated on top of the data which is lying on multiple nodes. Okay, now ideal size of an input split is the equal to the HDFS block, which means uh, we are essentially saying that whatever data is there, let it be handled by a single mapper. Okay, so as close as possible, if your input split is of that size, then it helps you minimize the data transfer. So input split size should be very close to HDFS block size. Okay, and this we know very well that Hadoop tries to run its mappers where the data is located. This is called data locality optimization. This is also we are going to discuss today. And from tomorrow we'll be discussing pig and pig Latin. Okay, tomorrow today will be the last class uh, on MapReduce. If all nodes hosting replica of data is busy, maps execute at the same rack, different node. This is something called data. We will talk about it very soon. Okay. So if all the nodes containing the data are busy, then map execute at the same rack but different node. If if even that different node is not available on the same rack, then we use another off rack systems. Okay. Tendency is to run on something very closer. All right, so this is what input split is. So let's talk about it in a little bit more detail. All right, so why do we require input split? All right, so if you look at the way HDFS is designed, it slices your data ruthlessly at the fixed boundary. Okay, irrespective of whether the boundary is lying in the middle of a word, middle of sentence, or middle of paragraph, or middle of um, wherever it is. Okay, so you can think of it this way. Say you are doing a word count, right? Say you are doing a word count, and your lines are too big. All right. So imagine your file is 150 MB. It contains three lines. Line 1 is of 50 MB, line 2 is of 50 MB, and line 3 is also 50 MB. Now, line 1, block 1 will contain line 1 plus line 2 and 28 MB of line 3, while rest of 22 MB will go to block 2. Okay? So, so your line is split into two parts. Okay. That is, but when we talked just now that whole line is provided to the mapper, then which means that this data from the mapper 2 should go to the mapper 1, or block 1 to block 2, the data transfer has to happen. Okay. So this is the reason why do we require input split, to basically have a logical representation of the data instead of having a hard boundary. Okay, is is it clear to everybody why do we require input split? So blocks are split on a fixed size, right? But logically, we require a different presentation, right? Like line by line, because each line can have different size, okay? Or in certain cases, sentence by sentence. So split is not on fixed size. Split is more on a logical level. All right. So is it clear to everybody? So feel free to ask because I'm seeing the silence which shows me that. Okay. Does the HDFS determines it? No. Okay. HDFS has cut the files into pieces which are of the fixed size. Okay. So HDFS doesn't decide the input split. Input split is decided by your mapper reducer program. If your mapper reducer does not define it, then the MapReduce library of Hadoop decides it. All right. Is this clear? Why do we require input split? Why didn't we just read block by block and start processing it? Okay. Okay. So a split will combine data from two blocks and send it to mapper as one line. Yes, you are right, Abhishek. Either combine or move to another one. There could be another situation where line 1 and line 2 lie on one mapper, while line 3 gets combined and goes to the second mapper. You're right. Okay. So P. Malik's point is that how can a Hadoop programmer define it? All right. So first you need to define your input split. Okay. So first you will define something called an input format. Before that, you will define something called a class called input split. Input split gives its length and knows about the location of the files, while while input format decides input format decides where are what are going to be the splits. Okay, and under the input split format, you will have something called create record reader. Record reader is the one which does maximum amount of work. Okay, so let me just show you where is okay. Okay, I think I have added it into my package. Okay, so the way it happens is first you define your input format. Okay, so right now I'm trying to create multiple line reader in this. So I extend a class called text input format. Okay, and the text input format basically does the line by line thing earlier. We are just trying to change that one, and there we say that create record reader, and under this record reader we just return our own record reader. This is the record reader which basically does your job of reading data. Okay. Okay, so Abhishek is saying in our previous result of word count, Files are cut intermittently. What does it mean intermittently? No, in word count example, our file I think was in a single chunk. All right. So this is how you should go through this example line by line. You will understand it in case you are interested in customizing the way the input is formatted. Okay. So you can define that. All right. So you should go through this example, which will be provided to you in the which is actually provided to you here, and also the sample project is here. You can download this sample project. Under that, you will see the standard map reduce with the other examples. Okay. All right. So those who are interested in going deep, you should go through this example. That should give you a good mm, amount of clarity. So in essence, we basically define something called input format, and in the stub driver, we define that our input format is going to be this. In stub driver, where is our stub mapper? Stub driver, and here we can say that job dot set input format class, and there we can say that n lines input format. That's all. Okay. So now instead of using the standard input format what was basically dividing your input line by line, and instead of that division of line by line, it will do the division based on our own logic, whatever we code in n lines input format. Okay. So you can have that look at that. They share to you. All right. Okay. So input is split. You can think of, yes, yes. Go ahead, P Malik. Set new checks is defined as for set number. Right, right. Here in this example, there is a different stub reducer, stub stub driver. Where is the stub driver? I can't see my driver here. Here. Just for this is a different case. It's a different example. Okay. So here, if you put okay, if you put set 4, then there'll be 4 reducers and it'll be run on parallelly. So the general thumb rule is if you increase reducers, what will happen is more data will get transferred. Okay. So more data will get transferred parallelly. If your data is smaller and your processing is also smaller, you should have one smaller number of reducer. If your data grows bigger and you have got too much of processing to be done, then you keep on increasing the number of reducer. Okay. Maximum number of reducer you should keep is equal to the number of nodes you have in the system, as in based on number of nodes you have on your cluster. Okay. Because there is no point in having more reducers than the number of nodes you have. It won't. Okay. Yeah, this is configurable. And there is no single thumb rule. You generally do a little bit of hit and trial after doing a little educated guess, and then you do a little hit and trial, and then you will figure out how many reducer tasks are appropriate for you. Okay. And also based on the numbers which Hadoop was printing, saying all the diagnostic information, then this is the amount of time which was taken in running the reduce. This is the amount of time taken in transferring the data. Based on that, you can take a call. If if your data transfer time is low, but your processing time is high in reduce, increase the number of reducers. If your data transfer is high and reduce task is taking too few time, then reduce the number of tasks. Okay. Now once you're done with that, all right, all right. So so input split is like is equivalent to a bunch of rows of your database, or you can think of a portion of a table is equivalent to input split, and the records are basically equivalent of a row. Okay. And basically each, in case of our word count example, each line was a record and bunch of lines were input split. Okay. So that was pretty much about input splits. You should go through that example posted on my courses. So using other programming languages, you cannot define input split the way you can define using Java. Okay. So whenever you have to customize your input split, you generally go for a Java kind of environment. In case you don't need to customize it, then it's good enough. Also, there are a lot of input splits available in the Hadoop from various places. You just download their jar and add those into library. So those input splits are available to you by default. Okay. Say for example, binary input split, in which whole file is provided to you in a single mapper. Okay. So those kind of input splits are available even if you are using other programming languages in which you do not have the option of customizing input splits. Okay. So moving on. Again, we are going to have a look at the data flow again in case of MapReduce, and then we're going to go to talk about a little bit more about partitioner and combiner. Okay. So instead of again me, you know, describing it, could you help me understand which portion of this diagram is not clear to you? This diagram shows you the data flow with a single reducer. Is it clear to you? Okay, Valentine is clear. Good. Okay. So here the important part is that input is split 0. This is created using the block 0. Block 1 prepare based on block 1, split 1 is prepared, block 2, split 2 is prepared. Although block 2 will not directly get translated into split 2 because some of the data from block 2 might go to block 1 and so on. Okay, so based on each of the blocks on the HDFS, these splits are created. For each of the split, for each of the record on top of a split 0, our mapper function will get executed for each of the record on the input split. And whatever is the output of the mapper, that will be sorted by the key in that output. And once that sorting happens locally, here the local sorting is happening. And once that happens and finishes, this data get copied to the reducer node. Okay. And that split is created by input split and reader class declared in driver. Exactly. That's right, Ajit. All right. Now the data gets copied. Here there is a merge happening, as you can see. And remember the merge will happen on this reducer node. Once the merge has finished, merge as in the key values, the keys and the various values get merged for each key. For each key, the values are merged. And once that happens, you feed it to. So each key and their values are fed to the reducer, and then reducer keeps on pushing it to the HDFS. All right. Now this is the diagram with a single node, and these thick lines represent the network transfer, while dashed lines represent the local transfer. And for, on each node, this is what is happening. The node is represented by dashed lines. Now, with the same representation, with the same legend, we have got another diagram where there are multiple reducers. Now, what you need to note in this diagram is everything is same. So on top of HDFS blocks, split was created. Out of it, input split records were created. On each record, mapper were run, and whatever output came from the mapper, from mapper key values will come, right? Key and the value, key and the value. That's what is going to come out of the mapper. Now, those keys are split into two buckets. Why two? Because there are two reducers in this case. Had there been three reducers, there will be three split happening here. Okay. So so if you have two reducers, say, and the input split has been decided automatically. So splitting of the output of the map will happen on each node, and this data transfer will start happening once all the mapper finish. So from the first node, first part will go to the first reducer, second part will go to the second reducer. Same thing will happen for other nodes as well. Okay. Same thing will happen for the other nodes as well. And once that happens, that merge will happen on both the nodes. And after the merge, the same process will repeat. Okay. So this splitting of keys into two buckets is based on generally the lexical order in which the order in which they will come alphabetically, the keys. Okay. Also, you can define your own partitioner. This is called a partitioner. Partitioning the output of mapper into buckets such that such that reducers reducers can be fed the appropriate data is called partitioning. Okay. So whenever you have multiple reducers, you create partitioner which will split your data onto multiple nodes or multiple reducers. Okay. Okay. Does shuffle happen based on the key? Yes. Shuffle as in the you mean merging, right? Sorting. Yeah, that happens based on the key. Okay. All right. So moving on. Okay. Now, how many reducers? By default, there is one. If you create too many reducers, effort of shuffling or moving the data is too high. If you create too few reducers, computation will take time because whatever computation you are running in reducers, that is, if that is not divided, then it will take time. Okay. So tune it to have the total number of slot. Tune it to have the total number of slot. Meaning, if you have say 10 nodes in your system, out of which your, I mean, barring one or two, you can have, if your computation is too high, you can have at most 10 nodes to run your reduce process. Okay. All right. So now let's talk about something called partitioner. Okay. So reducer will split. If you have more than one reducer, your keys need to be split onto these two reducers, right? Because, but one key can exist, one key can exist only on one reducer. Okay? One key can only exist only on one reducer. It cannot happen that we created two reducer and the one key for some values went to one reducer, some values went to another. That can never happen. Okay, that is by definition. So so to divide your data, because you know about your data more than Hadoop does. Therefore, you can define your partitioner better than what is there by default. Okay. When you know when you know that this is how your data should be divided such that your partitions of the data that go to various reducers are going to be equal. Okay. I mean, if you know that you can do a better job than Hadoop in dividing the keys which go to various reducers, then you should write your own partitioner. All right. Now the partitioner's definition is exactly like your I mean is basically like this. You are given a key and you have to tell which reducer should it go to. Okay. It should return a value starting with 0 to n minus 1, where n is the reducer. If you have two reducers, your get partition method should return either 1 or 0. If you have five reducers, your get partition method can return from 0 to 4. Okay. So your partitioner's role mainly is given a key, it has to give a number, nth number on which nth number on which reducer does your key need to go. Okay. So this is how it is done. So you have age partitioner. So as an example, you have age partitioner and your key is gender. So if gender is male, return 0, otherwise return 1. That's all. Okay. So all the keys which which have gender as M will go to first reducer, while all others will go to the second reducer. Okay, so this is how the partitioning is done. Like, okay, so this is that partitioner you can see here. Here I have done a little bit different thing. Here, first is your gender. For first value which is given to your partitioner. Basically, partitioner is run just after mapper. Okay, just after mapper, the partitioner is run on that key value, and for each key, it is for the partitioner gets key value and total number of reducers available to you. Whatever you had configured in your contact job saying that I need these many reducers, that's what will be made available to you. Okay, now this is my total number of partitions. Okay, sorry, number of reduce tasks. Okay, and this is my key. So all I'm doing here is divide the key with this. All right, so here is a different partitioner. So this partitioner was simpler, where I was just doing a percentage, and there is different partition I have written. What I have done in case of a word count, what I have done is my key is less than key's first character is less than k, then send it to the first partitioner. Otherwise, send it to the first partitioner. Sorry, first reducer. Okay, first reduce task. Okay. So is it clear to you? If you have to write partitioner, what will you do? Okay. Okay, good. Good. So you can write your partitioner now. If you do not define partitioner, it's okay. Hadoop does its own guesswork, and that's generally good enough. Okay. So let me just describe it again. So let's have a look at this. Okay. We have two reduces in this example. Okay. Two reduce tasks, as you can see in our step driver. Let me close this project so that there is no confusion. And all right, so I've closed every other project. Now you look at this partitioner what we have created. What it is saying, take the first character of the key, check if that character is less than k. Okay. If it is less than k, return 0, which means send it to 0th reducer. Okay. When we are counting in reducers, 0th essentially means first reducer. And return 1 means send it to the second reducer. Okay. Vishnu, is it clear to you? All right. So get partition returns integers, and the function parameters are the key and the value. This is the value for that key, and this is your reduce task count. Number of reduce tasks. Yes, exactly. So it is up to us to define which key pair has to go to which reducer. exactly. Okay. So lot of times Hadoop does a lot of guesswork. Okay. Based on the key, all it will try to do is see how it can divide the data. It does a lot of guesswork based on character ranges and very generic one. But if you want to optimize this process of partitioning, when you know for sure that this is how your data is divided, then you can go for this kind of thing. This is basically making a process faster and efficient. All right. Though partitioner can be written in any language. Okay. You can define in the streaming job. The streaming job accepts partitioner. All right. Now there is another concept called combiner functions. Okay. Combiner functions are really interesting concept. So as you saw in this diagram, that after sort finishes, the data transfer happens over the network. The copying of the data happens and then merge happens, right? What if before starting to copy the data, we could further do the processing and reduce amount of the data to be transferred? Okay. What if we could minify lot of data before copying it to the another system? And this data in the form of key value. Okay. So for example, in case of word count, what if we could do the word count on each node as well, so that the reducer does not have to do too many of word counts. Okay. So that your data transfer from each node for the merging r- comes down heavily. Okay. Like in case of our character counts, if we had counted the number of characters on the same node, it will be only 26 numbers that will get transferred in this copy from individual node to the merging. Okay. So that is where the combiner functions come into play. Okay. So these combiner functions are essentially run on the same node just after the mapper finishes. Okay. And they process the output of the map and help minimize the data transfer and does not replace the reducer. Okay. Their role is not to replace the reducer, and they cannot because they are run independently on each different nodes. All right. Now there is a the definition of a combiner is exactly like a reducer. The only difference in combiner is when we talk about combiner function, not every function can be a combiner function. Okay. Combiner needs to combine various values into a single value. Okay. Just like reducer reduces multiple values into a single value, combiner also does the same thing. The only difference with combiner is you never know how many keys a combiner will be handling at a time, and combiner is applied on the output of other combiners. Okay. So let's take a case. Say you have a combiner which basically counts the words. Okay. Or does the finds the maximum value of something. Okay. So let's say these are the four values, and our combiner all it does is finds the maximum value of these four values. So maximum of 0, 20, 10 and 25 is 25, right? So the maximum of 0, 20, 10 and 25 is 25. Now, either combiner function, in case our max is our combiner function, can be applied by Hadoop for you automatically either on all values or on partial list of values. So there could be a case where Hadoop applies first on first two values, then on next two values, and then whatever is their result, it will apply your combiner again on that result. Okay, like here maximum of 0 20 is 20, maximum of 10 25 is 25, and then maximum of 20 25 is 25. Okay, as you can clearly see, the result is same whether it is done this way or this way. The result is same, result is identical, that is 25 is same for both. Make sense to you? Which also brings us to the point that it could also happen that max could have been applied on two values, uh, maybe three values at a time or whatever. Okay, because bec- because sorry, our partitioner function could be applied on any number of keys provided by our mapper. Okay, and remember the combiner function also runs on the same node. Okay, it runs on the same node just after the sorting has finished or while sorting is in progress. Okay, so during the sorting is in progress, the combiner function is applied on the values. Okay, now which also brings us to the point that average is not suitable for becoming a combiner function. And why is it so? If average is applied on these four values all together in one single go, then we get an output of 11.25. That is the correct value. But if average is applied on first two values first, then on 1025 the second two values, and then whatever result we got, if we apply the average again, the result is 13.75, not 11.25. And if you apply average first on the first three values and then the next value, then the result is further horrible. You can see that, right? Is it clear to you? No? Shilpa? Sanjay? Harish? All right, all right. Great. Now let me see if it is really clear to you. Okay, what does it mean by this sentence? This looks little awkward, so let me put it defined. Okay, same signature as reducer. Okay, so when we are defining a combiner, basically the way we do it, it's not here. Okay, so you can see it, I'll show you. Okay, so you can see here. So this is our combiner. Okay, combiner extends reducer, and this is what the combiner do. Combiner is also, in this case, it's doing summation of values and giving it away. Okay, so generally the way people do it is that whatever reducer function they have, if their reducer function have this property have this kind of property, it is called cumulative and associative. So if the reducer function have the same value, they specify that use my reducer function as the partitioner also, sorry, as a combiner also. All right. So by default there is no combiner. By default there is no combiner at all. And while so not every reducer function can be a valid combiner. Okay, only those reducer functions which can be applied no matter how many times, still your output is correct, those are the valid combiners. Okay, like average is a valid combiner, max is a valid combiner. So sum, when you do sum is also a valid combiner. Now let's imagine that we have got this function, okay, which is essentially square root of summation of squares of values. Okay, so do you think it's a valid combiner? So question to you is, say you have a function which has a, b, c as the input parameter, and it returns the square root of summation of squares of these values. So is it a valid combiner or not? A valid combiner is no matter how you apply these combiner on the values, on which portion of the values, and then you again run it on the result until you get a single value. Okay, so the result should be same no matter how you apply a combiner on the values. So everybody is saying no. Are you sure? So this function ABC, function f, which is essentially square root of summation of squares of the values. So is it a valid combiner? So if you have ABC and if you apply on all three together, then your output is going to be this, right? What if you apply first on AB and then whatever result you get it, then you combine it together with C. So if you apply on first AB, you get square root of A square plus B square. Okay. And then whatever value that is, then you again square it and then sum it with C square. Okay. Which means the result is going to be A square plus B square plus C square. So I'll show you. Okay, so let's say we have a function a, b, c, and it is square root of a square plus b square plus c square. Okay, this is what we have. Yes, so if you apply on a, b first, and say we get a result called d, and then we apply the same function f, d, and c. Okay, so the result should be equal to f of a comma b comma c. Okay, then it's a valid combiner. What do you say? Or if you apply on first B comma C, and we get say E, and f of A and E should be equal to, this should be equal to f of A comma B comma C. Alright. So the point is that no matter how many times and how you apply a combiner function, if the result is same, then it's a valid combiner function. Okay, because you will not have this luxury in the combiner to get all the values in one single shot. So what is D here? Can somebody tell me what is D here? D is, quickly. Yes. So D is a square, not a square plus b square, square root of a, square root of a square plus b square, right? Now, and f of dc is going to be square root of d square plus c square, right? And which will become square root of, then square of d, right? Square of d is how much? Square of d is how much? A square, a square plus b square plus c square, right? So effectively it is equivalent to our first answer. Is it true in this case also? Is this correct? Anybody? So do you think now now do you think that f of a comma b comma c is a valid combiner function? This one, is this a valid combiner function? Awesome, great. All right. So next question to you is mean a combiner? Is mean a valid combiner function? Eh, So Ajit's question is, can we have both map and reducer on one node? Yes, definitely. That is how most of the virtual machine work. These are just processes and you can run multiple processes. These are the processors that run on different ports, and you can have run task tracker and all of this on one node. And also, even if you are having a network, then there are high chances that at least one of the mappers will be on the same node as reducers. Why? Because at least one portion of the data will not have to transfer to to a different machine, because if the reducer is on the same machine as one of the mappers, then at least we are saving something. Okay. Okay, so is mean a valid combiner? Anybody? Yes or no? Okay. Okay. Good. Good. So mean is probably not a valid combiner. Okay. Because it requires total number of values. Well, it differs on total number of values. All right. All right. And you can define your combiner like this. So when you have your driver, where is our driver? Here. You can say set combiner function like this. Okay. I had in a character count. Character count is a very good example where you can see a real value of combiner. Okay. Here in the combiner, all I did was did a summation again. Okay. It extends the reducer as you can see. All right. All right. Moving on. So that was our combiner. Now let's talk something about a little bit about what is data locality optimization. Imagine this, that there is a map task and there is a HDFS block. Okay, and there is one data center. Yes, we can do that, Vishnu. We can actually just use the reducer implementation as combiner also. Okay, here here instead of again defining combiner, we could have just said in our driver that use our stub reducer as combiner. That could have been good enough. Okay, it'll yield similar results. Okay, now so in this case there are three possible circumstances. Your HDFS block is lying on the same node where your mapper is going to run. Our map task is on the same node. This is the best case scenario and the luxury we all expect. But sometimes when the node is too busy, then we can have HDFS block on a on the same rack on the same rack but different machine. In this case, the data transfer will be over the network and little bit more costly as compared to the first example. And in the third case, the C, as you can see in the C case, there could be a scenario where your SDFS block is lying on one rack. Okay, rack you can imagine as a single Almira having the same subnet. Okay, containing multiple computers connected to a single hub. So the definition of a rack is all of the members of the rack are connected to the same hub. They differ only in the last digit, which is the last digit of the IP address. They are into the same subnet. And second, a rack basically contains multiple computers. Okay. So in case of C, you can see that the HDFS block is lying on a different rack. HDFS block is lying on a different rack. So that's the worst case scenario. Or maybe there is another data center. There is a fourth case also that there is another data center. The block is lying on one data center while the map task is being executed onto another data center. There could be these kind of scenarios. Okay. So the tendency of Hadoop is to try as much as possible to get the scenario number A, and then if that is not possible then scenario number B, and if that is also not possible then C is the option. Okay, so this is called the data locality optimization. So Hadoop tries to keep the these HDFS block and map task as close as possible. Meaning, it will try to get the work done onto the local machine so that the data transfer is minimized. Okay. Okay. So, uh, does it consider subnet? Yes. Can there be 65,000 nodes on the same B class network? Mm, no, because in a subnet you cannot have more than 255 computers. Okay, you will have to divide them amongst multiple racks or multiple subnet and then get it done. Okay, okay, all right. So you cannot have 65,000 node on the same subnet. Okay, unless you move to IP6 from IP4. Valentin, was I able to answer your question, or did I understand it wrong? Okay. All right. So now, quick questions to you. Can reducer take a benefit of data locality optimization? Okay. All right. No, it can't, because the reducer to input, if there is a single reducer, then the input to the reducer is from multiple nodes, and it can't really take the benefit of that. Okay. Second, so if you have to store a file with the replication factor of 3, on which all nodes will Hadoop store this file? Anyone? Local file on the first and second one. Local file for the first, second one to the other node in the same rack, and third one to the different rack. Good, good, good. So A, B, C. Good. All right. So yes. So the first one will be on the local node. Second one will be on the other node. Okay. So basically, the tendency is for first of all to keep everything for first copy on the same node, okay, on the local node. As in, say you are on Hadoop 2, you have copied your file from local system to Hadoop 2 locally. Now, the moment you try to copy this data to HDFS, it will immediately copy the first copy onto Hadoop 2. Okay. Whenever you're trying to copy to HDFS a file located on Hadoop 2, so it will quickly copy the data to the local HDFS node, and then it will decide on which all rack it will go. So generally on the other off racks, if off racks are not available, then it will store on different computers. So that's how the file storage keep on going, and these algorithm per se keeps on changing. They keep on modifying, and probably they must have changed it now by now. Okay, have to look at it again. All right. Now, how does Hadoop know about your network topology? How does Hadoop know that which computers are closer and which computers are farther? So general strategy is based on IP address, but you can customize it. So you can create a custom network filter to help Hadoop in that. Okay, you can tell that my IP address means this. So you tell Hadoop in terms of a sort of a folder structure. Okay, so the way you can see, you tell Hadoop that this particular node 1 is represented as S1 slash R1 slash N1. Okay. Similarly, node 2 means S1 slash R1 slash N2 and so on. That is how you tell my Hadoop that this is the name of my node instead of the IP address. Okay. Based on your scheme of things. All right, because there could be a scenario where your two racks or your two computers are lying in two different data center with a public IP address where you have no control over the IP addresses. If it is your local IP address, you can control them such that same rack have same IP address, everything. But in case you are having public IP addresses, it will make a lot of sense to basically be able to give the names to the node rather than only rely on the IP address. Okay, and that's where the network topology definition comes into play. So for each node you give the name to the Hadoop. Okay. Okay, so let's see. So you have got, say, one switch is connected to two racks, rack 1 and rack 2, and rack 1 contains these three node plus three node. Okay, this is the kind of network topology we are talking about. Okay, so Hadoop understands the network as a tree, not a map, but as a tree, just like a folder structure. All right. So here it says this switch 1 slash rack 1 slash node 1, switch 1 slash rack 1 slash node 2. So this is how we represent a hierarchy using a kind of a file system notation. Okay. Now, now the way you define it in Hadoop, the mapping, is by providing a script name which takes the argument as IP address and gives out a folder structure. Okay, a most simple one is replace dot with slash and the beginning of line with the slash. Okay, this is the one. And the way distance is computed between one node and another, so IP address of this one is defined like this, and this IP address is defined like this to Hadoop. Now we have converted our IP addresses like a tree structure. Okay, and even if in a data center you have a different scheme altogether, you can create this script file which will help Hadoop understand how is your data located, how is your topology structured. Okay, now the distance between one node and another node is probably the most important thing, and the reason why we are talking about all of this is because we want to compute the distance between one node and another. How do we find the distance between one node and another? Okay, now to find the distance is sum of the distances of the common ancestor, or sum of the distances between the parent and the child. Okay, now let's have a look at this. So distance between d1 slash r1 slash n1, d1 is data center 1, rack 1 and node 1. This is one path. So ideally they are not possible. Okay, we cannot have more than 4 levels in general, but in the tree wise you can have as many as possible. Okay, in the tree wise you can have as many as possible. Okay, though IP addresses cannot be there, but you can have your mapping such that you can define the trees. Okay, so you can have, I mean, the names you can define like data center slash floors, data centers slash floors slash rooms slash racks slash node name. You can have that, and that is Valentin, that is probably the reason why this aliasing is done. Instead of using IP address directly, Hadoop is providing you this way of aliasing so that you can name your nodes to fit into your structure. You can have to as many level you want. Okay, and the distance between d1 r1, so you have now two data center. Each data center has got two racks, and each rack has got these many rows. Now, so distance between first one is clear to everybody, right? So n1 and n1, the distance is same, 0. Okay, n1 parent is the common ancestor of n1 and n1 is n1, and the summation of them is 0. And in case n1 and n2, there are these two nodes, their common ancestor is r1 in the path. Okay, therefore the total distance between n1 and n2 is 2, not 1. Okay, so we have got n1, n2, n3. So distance between n1 and n2 is 2. Why? Because n1's parent is rack 1, r2's parent is rack 1, and distance between r1 and n1 is 1 plus 1, and therefore it's 2. Okay? Similarly, for for this, if you have another data center, another rack, and you have got node on it, so distance between n2 and n3, that distance is 4, because their common ancestor in the tree for n3 and n1 is r1. Okay, sorry, their common ancestor is d1. Their common ancestor is d1, and distance between d1 and n1 is 2, and this also 2, and therefore 4. All right. Now you have got absolutely different data centers. In those cases, the distance is 6. Is it clear to all? Or you can have it like here. So distance between this node and this node is 1 plus 1, 2. Distance between this node and this node is 1 plus 1, 2 plus 3 plus 4. Okay? This is how you compute the distances. Okay? Okay? So Vishnu, I don't know, but I'll do look at it. What are MPP databases? Okay. So as you can see that we first represented our node as this structure. Okay. So this becomes our topology. So we have got switch 1, rack 1 and node 1. So node 1 and node 2, their parent is rack 1, right? So distance between node 1, so I'm sorry. Okay, I'm sorry. Now let me explain the distance again. First, every node is represented like this path. Okay. Now, when we are computing the distances between two nodes, we first find who is their common parent. Okay. And then we find what are their distances from the common parent, and then sum of those distances is equal. Is the distance between the two nodes. Okay. So node 1 and node 2 has a common ancestor called rack1. The distance between node 1 and node 2 is therefore 1. Node 1 to rack 1 1 and rack 1 to node 2 is 2. Okay. Similarly, and also to you should note that distance between node 1 and node 3 is also 2. 1 plus 1. Okay. 1 from node 1 to rack 1 and thus 2 from rack 1 to node 3. So basically the distance of a node, summation of the distances between the node and its common ancestor is what we call the distance between the two nodes. Okay. Now node 1 and node 4. Okay. The distance is 1 plus 1 which is 2. Then we reach to switch 1 because that is what is common between these two nodes. And then we reach to rack 2 and then this is 4. Alright. So Abhishek, is it clear now? Great, great. So feel free to ask any question. And so today we discussed a lot about starting with input splits. Before that, we discussed how is it coded in Java. Then we talked about, actually today we talked about a lot of things. Okay, so we talked about MapReduce in Java, how to test a MapReduce in Java, then input splits. Then we talked about data locality optimization and network topology, rack awareness, then reducers. What do we do in case of partitioner, combiner, and all those things. So we are not going to cover joins in MR. The way joins are done is based on the example which we gave earlier. Okay. And basically joins are done only on a key or multiple keys, and that's all. Okay. So rest of the things we will be talking in terms of other languages, Pig and Hive. Okay. We'll be talking how to do most of the data churning using either SQL or using Pig. Okay. So those are the things we are going to discuss from tomorrow onwards. We'll not be touching MapReduce anymore. So yes, Manish's point is there a way to control on how much memory does mapper get or how many cores do you get? So probably you have not looked at this. Okay, you should look at it. Look at our Ambari from time to time. What is going on? Okay, is it good? Okay, Ambari service Ambari. St- Okay, so let me just do service Ambari server start. Okay, so Abhishek, I discussed the solution briefly. Okay, where I was actually explaining like this. You should also try it, and in case you get stuck, just let me know. Okay, so this was one of the rudimentary solutions. Okay, okay. So Manish, yes, there is a way to control the memory of each of the task trackers. Okay, there is okay, student, and then we can go to series one. All right, so you can have a look at this, and so like here you have yarn. Okay, so you can see that there is a memory we can define for node manager, resource manager, and you can control a lot of it. Okay, and by default, being multi-core or single is generally an attribute of our JVM. So while installing JVM itself, by default, it is generally multi-core. Okay, the JVM, and it's only the old ones before Java 6. Those were not multi-threaded. Right now, you keep on using your student's account without any worry. Okay, because as I'm creating independent accounts for all of you, it's actually becoming too much of management headache. Okay, because we have to create SSH accounts for all of you, then Hue and Ambari accounts, and then give permissions. Okay, and but if that gets automated, few things are left. If that gets automated, then I love to give you the separate accounts. Yes, we are using V2. Nobody uses MapReduce version 1 anymore. All right. We are using MapReduce version 2, 2.0, and because nobody uses it anymore. Nobody uses 1.0 anymore. All right. Great then. Attempt your problems, finish the assignment. Even in the plain English, it will do, and even in the plain, pseudocode, it will do. So, howsoever possible, please finish all of that. Okay. Any other questions? Feel free to ask. So, how is release management of mapper and reducer done? Okay. So, release management goes just like your standard Java code. You have your basically a repository where you keep on committing your code, and you give a particular tag whenever you are releasing. You give a tag to the release managers and let them ship it to the various servers and then execute it. Okay, so that's the general model, and there are I think and basically what people do is they put the Hadoop. itself into the ant tasks, and or OG task into ant task, and then launch it. That's another way of release management. All right. So every node, you don't have to worry about that part, because so your problem is that this Hadoop.jar, whatever jar we are creating, it need to be made available on every node, right? So you do not have to worry about it. The moment we say Hadoop jar, and you say this is my jar file and these are the libraries I want to ship, it automatically does it for you. You do not have to worry about that, to keeping the nodes in sync. All right. Yeah, yeah. So the good part about yarn is that we do not have to worry about yarn as such. Okay. The yarn is basically an internal change. Yarn is basically an internal change and minor nomenclature tweak. And basically, it's an internal infrastructure change. If you are interested in contributing to Hadoop or building something like a MapReduce on top of Hadoop, then yarn matters a lot to you. Okay. All right. So far we have been using the common classes and not the yarn specific one. All right. Example of MapReduce from your previous work. Okay. Okay. So in my previous work, there are basically two kinds of MapReduces I did. First one involved First one involved cleaning up lot of log files. So we had these 200 terabytes, close to 200 terabytes of log files, from which we wanted to extract all the people who are playing games. So whenever people are playing games on their mobile, so and there is an ad being displayed, so a query comes to the ad network. So let's say we were the ad network at InMobi, and a lot of users, when they're playing game, they actually see our ad, the ads which we are pushing. So all of the requests which are being made by the app was coming to our server, and we had all of these logs in the Apache log. Okay. And these logs were made available onto the network. So fortunately, I did not have to do much in terms of moving the data. Moving the data was mostly the Flume jobs which were running all across our servers. After that was done, we had these nice Apache logs which need to be cleaned up, and we had to figure out which user accessed which page, and we had to remove certain countries in this data. So we wrote a map job which basically picked up line by line from Apache logs and cleaned up the data in terms of user id, ad id, user id, and user id, game id. So which user was playing which game while they accessed our server, those were the only records that were retained. Now, once this was done, this map task was done, in which we got a clarity that this person was playing this game. Okay. Once we got this clarity, what we did was we we formed the statistics like this person likes this game this much. How is that possible? By forming the key as user ID and user ID and game ID. Okay. When you form the user ID dash game ID, you will have, and then you sum up total number of times he has played, which means we have got a number saying these are the people, this person likes this game maximum, this person likes this game this much, and so on. Okay. The next step, once we got the counts of all the people playing the game, the next step was to normalize this data. How did we normalize? We first computed what is the maximum times a game is played. Okay, and then we divided these numbers, and all of this was based on MapReduce. So at the end of the whole process of multiple MapReduce, what we got was user id user id game id, and then a coefficient between 0 to 1 saying how much a person likes a movie. Okay. Likes a game. Okay, not movie. How much a person likes a game that we had put. So you got the idea, right? So we had Apache logs of this form. You can say, I'll just show you how does an Apache log looks like. So though we are going a little over time, but let's just do it because here it is important. So let's say, how does Apache log look like? So if you can see, the access log are like this. So these are the access logs of our website. So you can see that most of it is quite a junk. Okay. But you can see that here you can see this line. It shows to us that this particular IP address has accessed this particular URL at this particular time. Okay, and if you can see that it's basically a Google bot. The Google bot came and looked at our forum. Okay, this particular forum, right? So based on this, we can deduce a lot of things. But in our case, these requests were coming from the app which was embedded, and we had to convert this into something like user 1 likes to play game 1. Okay, user 1 has played game 1, user 1 again played game 1, and so on. And there we did other kinds of filters also that remove all the data from this time to this time, all those kind of things. Now at the end of it, we came to know, first was forming this key value. Okay, who played what? This was one. Second was who played what, how many times? How many times? Okay, that was second churning. The third step was to figure out same thing but normalize. Okay, normalize. Okay, okay. So who likes which game, how much, and how much. Okay, so all of this we did using our MapReduce only. Okay, once we had this rating in place, one u1 likes game 1 and it's zero point 0.6, and u2 likes game 2 and we say zero point 0.8, and so on. So we formed this. Now we gave it to Mahat. we gave it to Mahat, and Mahat gave us a recommendation saying user would user 1 would like game 2 4.4 times and so on. So this is what I did in case of my previous experience. Okay, there were a few more examples I have, but this is the most simple one I can give you. Okay, sounds good to you? Okay then. Okay then, have a good day and feel free to get in touch if you have any questions. And I've got really good feedback from your class, and keep that feedback coming in. Okay. Yes, this is what people call it recommendations. Yes, yes. All right. Great, great. Thank you for wonderful questions. And please start working on your assignments because there are lots of more assignments coming in, and that will become a little overhead. Okay. Bye bye. Have a good day, you too. And see you tomorrow. All right. Bye bye.